I'm very happy to be here to share some work that have been done during the Innovine project about modeling the growth and quality of grape berries in changing environments. I will share my time with Rami just beside me. So we know the berry quality is a very complex trait, which is very well introduced by Marcus, and is very essential to the wine quality. And when we're talking about the quality, in fact, it's mainly about the chemical compositions inside of the fruits, like sugars, organic acids, secondary metabolites, and which will determine the wine quality, like the alcohol content, the flavor, aromas, and the colors. And in fact, not only the content is important, the balances between different components or the composition of different metabolites are also very important. And those berry quality, in fact, is a result of the interaction of the environment and the genotype. For the environmental aspect, we can see the climate conditions, the soil, and also viticulture practices, what cultivar we use, and also all these decisions or conditions will determine the plant processes like the photosynthesis, transpiration, and also, of course, all the metabolism pathways occurred within the berry. So as we mentioned several times, the climate change is modifying those conditions and then finally consequently modify the berry quality. So as I give you two examples, the first one is about the sugar concentration. Over the last 20 to 30 years, we saw a continuous increase of sugar concentration, then translated into alcohol content. And this might be due to effects of high temperature. And of course, there might be other factors influence those increase. And also, we know, we well notice that the high temperature, very often they can reduce this anthocyanin, which is the color pigments in the wine. So we can see the berry quality is determined by a very complex system. So to better understand the response of these complex traits, we think it will be useful to develop some holistic approaches like modelings to understand the variability or the regulation to provide more reliable predictions in changing environments. If we summarize a little bit the major processes or factors that are involved to determine the berry quality, we can say we have a component of the canopy part for the shoots, which will provide water, will provide carbon sources, and also some nutrient. And then those processes will be affected by the cultivar, the genotypes of the grape, and also the environmental conditions. And of course, there are many biochemical activities will happen inside of the fruits to determine the berry growth, the metabolism, primary metabolisms, and the secondary metabolism. To start with this, we developed the model focus on the canopy part. So I will let Rami to continue the story.
I'm here today to present our part of work in this working package. At Montpellier, we were concentrated rather on the effect of complex canopies on water-use efficiencies, while at Bordeaux, they were rather concentrated on the berry development and related issues. So at the base, we wanted to produce a model that accounts for different grapevine canopies that we see quite often in vineyards, like the vertical positioning system, the Lear system, and the Geneva double curtain systems. So we looked for models that account for such complex canopies on net photosynthesis, on gas exchange, on transpiration and temperature. And we finished by building our own model, which takes into account three basic points. The estimation of intercepted light at the leaf scale level, the estimation of water availability at the leaf scale, and its temperature. So we built the hydroshort model, which accounts for these three aspects, which takes the canopy as an input, estimates interception, estimates gas exchange, and then through three integrated loops, we estimate the water availability at the leaf scale, we estimate net photosynthesis and evaporation taking into account water deficit, and then we estimate again gas exchange based on the water level and the temperature. So I'm just going to do a brief description of the three lights, hydraulic and energy modules without going through equations. So our light interception model is based on the Caribou model, which is produced by colleagues from the INRA, which takes, considering that we have an external solar light, we distribute our light into diffusive light, which comes from the sky, based on the sky overcast level, and it also splits this light source into direct energy, which comes directly from the sun. So each element within this canopy, we calculate its irradiance level based on all intercepted and transmitted energy from each element in this scene. So once we estimate the intercepted photosynthetic flux density, we use it to calculate the potential transpiration, which is then used to estimate the water potential of the xylem. So we estimate what we call the hydraulic structure, basically on the classical approach of Ohm's law. So we consider our canopy as a system of resistances and transistors, and calculating the flux which goes out, we go down, we calculate the flux at the color, and then by imposing a lower boundary condition at the color level, we go up and we calculate the water potential at each element of this canopy. Then once the water potential of the xylem is estimated, we calculate the energy balance of the leaf, of each individual leaf, which is a novelty in this model based on recent research conducted by Vincent Guccic. So each leaf receives, the energy balance is calculated for each input in the visible and the infrared bands, in the thermal bands, and then it loses energy as a result of thermal radiation, as a result of transpiration, and then as a result of heat conduction between the leaf surface and the surrounding leaf air masses. So just to give an example, because we have not finished the calibration yet, to give an output of what we could obtain to provide inputs to models developed with Zhanwu. Here we have these three canopies with their interception of the incident irradiance through diurnal courses. So we can see here, that we capture effects of canopy structure over intercepted light compared to the global incident light, and and then when we use it to estimate net photosynthesis and evaporation, we see that, as classically seen, the opened Geneva double curtain structures produce the most of net photosynthesis, but in revenge we have a great loss of evaporation. So at this level we can't say which kind of structures produces the best water use efficiency, because our results are not yet calibrated, but we can just say that the model produces, for the time being, logical results. So in the future, we want to calibrate with Zhanwu to couple the our gas exchange processes with the berry development process. Thank you.
As you notice that in the model of honey, there's no berries considered. So we in Bordeaux we continue to make a focus on the fruit berries and try to include the berry growth and sugars and other secondary metabolites. To do this, we develop a grapevine XL model, which is also a structure function model. But since the canopy is so complicated, so we started with a simplified system, which we called it fruit cuttings with one single shoot, one cluster, and a simplified root system. And the functional structure model represent all those components with their corresponding biological processes. And this model has 4 modules. The first one is leaf gas exchange, the second water flux, and then carbon flux. These 3 modules will provide information to the berry growth module, like xylem water potential and the phloem sugar concentration. And so during this project, we calibrated the model with different data set. So now the model can capture the effects of CO2 concentration on photosynthesis rate and the different light density on the photosynthesis. And also it can well represent the effects of water stress on photosynthesis rate. And for the water transport module, we use a Dardu-Davis model that take into account the biochemical models, signals, and also hydraulic signals. And after calibration, the model can well reproduce the negative effects of water stress on the transpiration. It can also reproduce the effects of water stress on the AB concentration, AB production in the roots of the vine. And so now I will move to the berry growth. For the berry growth, we use the information from the above 3 modules about the sugar, the sugar gradient and also the water gradient to calculate the water balance and the carbon balance, as mentioned by Marcus. So for the water balance, we have some water coming into the plants and also some water loss due to transpiration. And for the carbon balance, we have the carbon imported from the plants, and then some carbon will be used by respiration. All these processes have been taken into account in the model. And after doing this, the model can reproduce the effects of leaf-to-fruit ratio in our simplified system. For example, when we provide a very low leaf-to-fruit ratio, our fresh weight and dry weight were both reduced, and the model can reproduce these negative effects. And we can also use this model to make some virtual simulations to verify. For example, here is if we increase 5 degrees of the temperature, and we saw a big drop for the fresh weight, but a very small drop for the dry weight, which will translate to a different sugar concentration. And then for the sugar concentration, we also developed something to model its effects. We use the fresh weight and dry weight as input, and then decompose the sugar concentration into 3 components, which is the sugar importation, and then the sugar metabolism, and then the water. Of course, the water can dilute the sugars. And by doing this, we can run the model for a quite big data set, which cover 15 years and for 3 representative cultivars at Bordeaux. And as we can see here, the simulation and observed value are agreed quite well. And those are the primary metabolisms, and also we know the secondary metabolisms are also very important for the fruit quality. So we tried to look at the color pigments, mainly the anthocyanins, as we can see here. In fact, the anthocyanins can be very different between different cultivars, and also it can be affected by many environmental factors like high nitrogen, high temperature auxins will reduce the anthocyanin, and sugars, high light will increase anthocyanin content. And also the composition of the anthocyanin is very important because the different component can give different colors. So we just simplify the metabolism pathways and represent it with simple mathematical functions, and then we arrive to well reproduce the effects of light. In fact, when we remove light from the clusters, we saw a big drop of anthocyanins and also the modification of the composition. And of course, when we compare, verify the models, we see quite good agreement between the modeled and the observed pattern. So just to give a brief summary, during this project, we developed some work at fruit levels to simulate the berry growth, the sugar accumulation, and also the anthocyanins. And at the plant level, we developed 2 different structure function models for gas exchange, water transport, and also the berry growth. And in the future, we think we will continue the work in 2 directions. For the fruit part, we will try to include other metabolites like organic acids and also like different aromas. And maybe at the whole plant level, the first thing we want to try is try to connect the complex canopy model with the berry growth model, and also maybe integrate the berry metabolism modules into those complex the models. And maybe I didn't mention at this moment the shoot. We have a static canopy, and in the future we want to model the shoot growth with this functional structure model. And that's it. Thank you for your attention.